Hello, everyone. We'll wait for a minute or two as people join. Hello, Hannes. Can you see my screen and hear me okay? Thumbs up there. Very well. Let's get going. Good morning, good afternoon, good evening, everyone. Thank you for joining us today. Welcome to this webinar, which is part of the ongoing series hosted by ISO Technical Committee 347 on data-driven agri-food systems as part of our commitment to transparency, engagement, and inclusive participation in the standards development process. ISO TC 347 is a relatively new and definitely ambitious committee working to develop international standards that enable trustworthy, inclusive, and effective use of data across agri-food systems. My name is Andres Ferreira. I'm the chair of TC 347, and I'll be your moderator in today's session. Our webinar series is designed to explore key technical areas where standardization can support innovation, sustainability, and interoperability in agri-food systems. Today's topic is pay attention if you want it to work, the case for machine-actionable unit of measure codes and QUDT. It relates to perhaps the most fundamental issue in data-driven agri-food systems, which is how to represent and preserve the meaning of the things we measure. Using units of measure and the codes that enable computers to represent and preserve those units of measure. Today, we'll describe how units of measure and their digital representations work, describe what the industry's done in this space and why we're at a crossroads, introduce the QUDT system of machine-actionable unit of measure codes and the ontology behind them, share a simple proposal of related action within ISO TC 347, and show how you can actively participate in shaping upcoming international standards. The session will be recorded and will be made available after the webinar. Please feel free to post your questions either in the Q&A box or in the chat. We'll address as many as we can during the Q&A segment at the end. So let me introduce our speakers. We're very fortunate to be joined today by Dr. Steve Ray, Ralph Hodgson, and Fredrik Falda Antonissen, who will lead us through today's discussion. Steve Ray is an independent expert in the use of ontologies and formal representations to ensure unambiguous definitions of terms and relations, particularly for interoperability and standards in the smart electrical grid, the Internet of Things, manufacturing, and medical devices. He has a 27-year track record of initiating and leading R&D projects related to information standards at the National Institute of Standards and Technology in Gaithersburg, Maryland, followed by a decade as a distinguished research fellow at Carnegie Mellon University. He has ample experience leading and participating in standardization efforts, and he's currently the CEO of QUDT.org, a nonprofit founded to provide semantic specifications for units of measure. Ralph Hodgson is currently retired from his position as co-founder of Top Quadrant Incorporated, a software company specializing in data governance solutions, semantic web technologies, and ontology engineering. Prior to Top Quadrant, he was executive consultant and founding member of the object technology practice in IBM Global Services. He started a PhD in high-intensity magnetics, but then following his employment at Hewlett-Packard, he completed a Master of Science in Digital Electronics and holds a first-class Bachelor of Science with honors in Physical Electronics. He's consulted with NASA on ontologies for the Space Shuttle and the Constellation program. He's the president and ontology architect for QUDT. Finally, Fredrik Falda Antonissen is CTO at the POSC-Caesar Association, where he leads the development of digital services and reference data libraries that support international standards, interoperability, and trusted industrial data exchange. His work focuses on turning complex technical standards into practical, scalable solutions that enable collaboration across organizations and supply chains. Frederick's background spans climate change startups, critical banking infrastructure, and industrial data platforms, combining deep technical expertise with experience in governance, standardization, and cross-industry collaboration. So let's get started with this topic, and I'll briefly introduce it and then hand it off to our presenters. So what are units of measure? A unit of measure, and we'll abbreviate it with UEM in a few parts of this presentation, is a standard way to tell how much of something there is. Units of measure help us measure things like length. So how long is something? And we use units like meters, feet, millimeters, and so forth, or how much stuff we have, the mass of something in kilograms, pounds, grams, or time, how long did an event last? We can measure in seconds and hours. Or volume, how much space does something occupy in liters or gallons or cubic meters or things like that. For example, if you take a pencil and you say it is 19 centimeters long, well, you have a value there, the 19, and then you have a unit of measure, which is centimeters. I think the take home here is that units of measure help different people that might be talking about the same pencil understand the measurement in the same way. Just to drive the idea home, let's talk about a horror story. Mars Climate Orbiter, a wonderful project that NASA had several years ago to the cost of $125 million. And it's this large spacecraft went all the way to Mars, and it was meant to orbit the planet and serve as a communications relay for things happening on the surface with another probe. The problem is that the NASA team at the Jet Propulsion Lab used metric units in their calculations, and then the manufacturer, Lockheed Martin Aerospace, used the English system when providing them data in real time to feed those calculations. The end result was that the spacecraft crashed and burned as a result of assumptions that were being made about units of measure. They were being treated implicitly right? This number must be in such and such a unit of measure. Wrong. It was in something else. So, what are machine actionable unit of measure codes that I mentioned earlier? Well, they're short labels. A unit of measure code is a short label that represents a unit of measure, like, kg for kilograms or uh, meter or something like that, that you can use again and again and again um, conventionally to represent a unit of measure. What makes the machine actionable is if a computer can read and understand them unambiguously. Why is it important to have machine actionable unit of measure codes? Well, because we're interested in sharing data among different computers. And machine actionable unit of measure codes help preserve the meaning of measurements as their results are shared, because different computers can interpret the 19 centimeters in the same exact way. I think that as an industry, we need three things in a set of machine actionable unit of measure codes. We need a stable, extensible representation. So we need codes that will always be the same, preferably compact codes, so that we don't eat up a lot of bandwidth moving them around, with a simple and transparent governance mechanism. So if you need to add one, right, you know what to do. The second requirement is that we need the system to provide guidance and also the conversion factors to support unit of measure conversions. If you have something that's being given to you in degrees Kelvin, help your computer convert it to degrees Celsius, or if you're getting it in feet, convert it to meters, or if you're getting it in, kilograms per hectare, to be able to change it to uh, grams per square meter or things like that, right? And the third requirement is that we can use it for reasoning and to compose and decompose results from math. So if our calculation produced a number in, meters and like how what distance was covered by a machine, and then we have another number that's the time during which that machine covered that distance, that then we can calculate and express with another unit of measure code the speed in meters per second, for example, right? So an example, let's imagine we've got 10 meters covered during 2 seconds. So we're doing math. We've got a 10 and we're going to divide it by a 2, and we have a code for meter and a code for second, right? So the result that we want is 5 and a code for meters per second. And this is an example in the adapt code set of what that would look like. Okay. How has the industry done it so far? Well, one example is what's been done in ISO 11783 Part 10, what we lovingly call ISO XML. There, the units of measure are implicit. There's a code. Let's stick to this idea of speed, where we've got a code that's a 397, and that represents the actual speed of a machine. Now, those values are assumed to be in millimeters per second. So if you're ever going to use that 397 key, the value that goes along with it has to be in millimeters per second. Nobody tells your computer this. You just have to know it, right? By reading the documentation. So a way to encode that would be like if we started with the 5 meters per second, right? That's 5,000 millimeters per second, and then we'd encode it as a key value pair of 397, that means the actual speed, and 5,000, which is the millimeters per second. Okay. Second example, a more recent one, is with the Agricultural Data Application Programming Toolkit, Ag Gateways Adapt. There, units are implicit in the data in the new adapt standard, but explicit in the data definition. That means is that just like ISO XML, when data travels around being exchanged, the units of measure don't go with the data. There's a key for, say, speed. And then you can look up, your computer can look up the data type definition and see that the unit of measure is such and such, right? In this case, a meter per second code that we'll see in a minute. So the good news is that the unit of measure is machine actionable, right? The definition is machine actionable. So our 5 meters per second would be encoded as speed 5.0, right? Speed is the way that key is encoded in adapt. A third example, which is from the 7673 Part 2 standard project, for example, is where units of measure are explicit, but you have options. Every observation has a value, normally, along with a unit of measure code. But you do have 4 options. UN Recommendation 20, Universal Codes of Unit of Measure, QUDT, which stands for quantities, units of measure, dimensions, and types, and adapt, right? And so in this case, you've got a key for device speed. There's that VR vehicle speed. And then the 5 meters per second would be, if you used adapt as your options, would be VR vehicle speed, then the 5.0, then the code for meters per second. Okay. So this is how we've been doing it, but we're at a crossroads. Adapt, which was emerging as a really interesting option, is just getting out of the unit of measure code management business, because it's been transitioning from an adapt framework that included conversion codes and math and so forth to the adapt standard that does not, because it's simply a schema. The 7673 team has been veering away from trying to be all things to all people and is looking to converge to one option, at least one default option. And ISO TC 347, as we're getting started with our own standardization efforts, needs a clear solution for its standards. So let's put some of the options, like the 4 that I've mentioned before, together with the rules, right? I made this little table that shows how the different options meet these different rules. They generally work fine with rule number 1 about the stable, extensible, transparent governance and the existence of codes and so forth. If you get like a so-so sign here with UN Rec 20, is that one time that I tried to put in a couple units, it sort of got lost in the conversation. They have a process, it just didn't work for me. But that doesn't mean that it doesn't have it. Rule 2 about supporting unit conversion math. Currently, QUDT is the only one that does that. And the third one that supports composition, right? QUDT does that, and it does it better than the others, because the way it's set up, you can, for any given a unit of measure, like meters per second, there's only one way to represent it, right? With some of the others, you could have it, meter to the first power times second to the minus first, or backwards and things like that. And that makes it harder to use those units computationally, right? So now we're going to look deeper into QUDT, and that's why we have our guests here, right? So Ralph, I'll hand it off to you.
Very good. So I hope to be heard. My voice is being heard. I just have a check on that. Yeah. Okay.
I can hear you fine.
Okay, good. So I'm wanting to go to the next slide now.
And
Um, so if we move to this, the I was very fortunate to work at NASA. Actually, worked there from 2002 to 2012 as a consultant from the company I created, Top Quadrant. The response to many of the things that were happening there, the I think Fred, we heard the motivation about the Mars orbiter, but there were other things that led to NASA getting very involved with interoperability, particularly between simulation systems and what are now called digital twins. In fact, there was a lot of work of that kind started at the time of my presence at NASA. The motivation for this led to a lot of insights into how to represent the distinctions between quantities, the parameters of a vehicle, such as the thrust, the force on a reaction control system, the distinction between a more interesting example of the speed of your car. An easier example is the speed of your car is a velocity, but it's a quantity when it's associated with the car. This gave me insight and my team insight into the distinctions between quantity, quantity kind, and unit. And that motivation led to a lot of modeling. And we did this modeling in OWL, the ontology web language. That started in 2008. Since then, we've moved to Shackle, which is a constraint language. A model is a set of constraints, and Shackle can be used for modeling as well as expressing data. And the insights, I come back to that at NASA, have given a lot of foundation for the distinctions of how to have unique identifiers. On the space station, they're known as one thing. On the launch vehicles at NASA, they're called PUIs. At the time we were working on constellation program, we had to create another short way of speaking to that, compact unique identifiers. And this led to the need of a document, which you see on the right, to describe all of this. And NASA is a document-centric um, organization at the time, um, caused some challenges in how to have our models generate these documents. But putting all that history aside, QDT is now has a life of its own. It's grown beyond the use in America to the use internationally, and it has a large adoption, which you'll hear about in these slides. I'll end by saying I'm very gratified to be talking about this after such a journey it has had, and it's a pleasure to be talking to the TC 347 people. I've had experience of working with ISO before in manufacturing when I was in the manufacturing sector 30 years ago. So it's a pleasure to be reconnecting to ISO. Thank you. And I'll hand, I think, now to Steve Ray. Yep.
Okay. Thank you, Ralph. All right, so let me get right to it. Whoops, there's what is QUDT .org. We're a nonprofit, as Ralph had mentioned, and we're basically our objective is just that, limited to units of measure for anyone to use. They are available as web pages for humans at that website, but as Andres had mentioned, more importantly, as machine interpretable concepts in a variety of languages based on the OWL and the Shackle schema languages. What it can be used for is, as it says, unit conversions, transformations. We have a variety of, you can read the tiny little print on the right there, libraries that others have written in JSON for JavaScript or Java to incorporate the QUDT ontologies into your applications. It'll do error detection, and as Andres implied, it's dimensional analysis is a very powerful tool to make sure you're not trying to compare a temperature to a length, for example. That would be dimensional analysis. Okay, diagrammatically, if you like, these are the core concepts. The unit at the bottom there, the quantity, which is in the context of the speed of the car or the volume of irrigation. Um, the value is the number, and then the quantity kind is what is this? Temperature, length, as Andres had said. The dimension vector, that's the dimensionality, which we have a very compact way of describing that. So in your actual application, you would have a quantity like my thermostat setting, value of 72, and it has a reference to a unit, which is in this case, degree Fahrenheit, and that is a unit for a thing called temperature. That's the quantity kind. So there's the quantity kind, the unit, the value, and the quantity. Okay, that's those same concepts. So let me step back and sort of look at, so what is this QUDT stuff? How is it built? What does it do? One thing we insist upon is it's FAIR compliant. For those of you who know what findable and accessible, interoperable and reusable, that's FAIR. It's two versions of a schema, owl and shackle, with a bunch of vocabularies of units, quantity kinds, dimension vectors, etc. Actually, that units is up to close to 2,900 now. It's always growing. This is the point about these URIs, these persistent and unique identifiers, which are both in our files we distribute, but also on the web. So they're resolvable. In other words, you can type in one of these URIs, like it says there, with an A at the end, into your web browser, and you're going to get presented a page for a human to read, or it uses a technique to do content negotiation. So that if you're a machine asking that same URI, it'll send you a snippet of code, basically, that you can then compute with. We have a very well-defined grammar for the names of these units. That is very important because it gives you an idea of what a unit means when you're presented with the code. Some people have Wikidata, for example, just uses a serial number, which is fine if you're a machine, but it means when you're manipulating these things, you really don't know for sure if you're using the right unit or not. These are all Turtle, RDF, resource description format, etc. And we're open source licensed, free to use. You can incorporate it into your commercial software, whatever, without royalties. So we feel strongly about that as well. Just a little bit of indication of uptake on this. This is GitHub stars on the left. It's a continuing growth curve. I did a quick Google Scholar search of papers and documents that reference QUDT. I actually just did a refresh on last year. It almost doubled from the 2024 number. I didn't update the slide yet, but it's definitely on the rise. Of organizations. We have standards bodies who are adopting QUDT and using it in their work. We have, and you can, of course, look at these slides later, so I won't dwell on the individual things, but it is internationally used. This is a small subset of the organizations that we are aware of that are using QUDT, although given the number of of papers that have been talking about it, and we can't really tell who else is using it. It's open source, so anyone can download it. We don't know who those people are, but these are people typically who have interacted with us with questions or endorsements or whatever. So organizations, standards bodies. I mentioned earlier that there are other people who have built libraries based upon QUDT. Here are some of them that we're aware of in Java and JavaScript, but also various repositories and registries list QUDT as so that it's findable. That's part of the F in FAIR. So we're growing. And with that, I'm going to pass the baton over to Frederick, who is with PostCaesar Association, which is, we are basically merging into PostCaesar this year. So for sustenance, if for sustainability, maybe that's the best word for that. Frederick, please take it away.
Thank you, Steve. So, hi everyone. My name is Frederick, working as CTO at PCA. And PCA, as I think you mentioned, Steve, stands for POSC Caesar Association. We're a non-profit membership association, and we're based in Norway, in Europe. And PCA's mission is to connect information, and we want to connect it across people, systems, organizations, and also industries. Now, a key to our mission is standards, and they're also key to efficiency and quality within industry data exchange. But today, many standards are still published in non-software friendly formats. For example, Excel. That means that different companies takes the same standards, downloads them, and then implement them in their own ways. And that kind of defeats the purpose. Value gets lost, especially across organizations. And at PCA, we solve this problem by publishing standards in a software-friendly way. We provide one common implementation that everyone can use and reference. As you can see from this illustration, this is not, let's say, it doesn't cover everything, but you can see here that we do provide a wide variety of standards, and we believe that to be a necessity because a standard can't cover everything. And for example, you can see that we are I guess you can't see it from this illustration, but in any case, there is a box on the left-hand side that says IDO and SDO. Those are coming ISO standards, and we are an ISO-appointed maintenance agency for those. For other standards, we have other arrangements, and then we also have QUDT, which, as Steve mentioned, we are now working on merging into PCA. And QUDT will be made available through an integration to our platform, but it will still be available as is today as well from the GitHub repo that is currently openly available. And that's going to stay the same way going into the future as well. So with that, Steve, could you go to the next slide? Mm-hmm. Thank you. So if anyone has ever told you that a standard is either perfect or finished, I will state that they are lying because we don't know what comes tomorrow. And business needs emerge with time. They emerge and they have a very different, let's say, schedule for being fulfilled than the traditional standardization cycles can provide. So there is a need to support emerging business needs, but also balance that with the standardization processes that exists today. And through our platform, we provide that balance. Users can propose extensions or other content that builds on the standards that we provide. And as long as they pass entry-level technical quality checks, they're made available and usable instantly. When things have been put into our platform and pass that initial check, they go through a collaborative review process where we bring together parties from different organizations to review and ensure that whatever is being proposed actually makes sense from a domain perspective. If something isn't accepted, it's marked as rejected, but it still remains available. And the very important part about that is that you can then fulfill your business needs as they emerge without taking on a technical risk. And then if something is in fact rejected, you can merge over to whatever is pointed to as being applicable when you're ready to do so. And I believe sincerely that that is a good way to strike a balance between those two needs. And as you can see from the diagram on this slide here, we are going to apply the same process to QUDT. It's not exactly the same from a technical perspective because we are integrating with GitHub, QUDT's GitHub repo. But in essence, the process itself will be the same, and we will still have a QUDT committee managing those changes that are put into the system. And just as you can propose things through the PCA platform regarding QUDT in the future, you can still also propose things directly through the GitHub repo. And with that, I think I can pass it back to you again, Steve.
Okay, sure. And I just add a coda to what Frederick said is that we might have skimmed over it, but our merger with PCA is not just technically incorporating the QUDT models into their framework, it's also an organizational merger. And we're doing that to assure that we're not going anywhere. We want to be available, and it's we're not just going to pop out of existence. We will have this whole association behind us with their own infrastructure. So we wanted to make sure that we don't just build this thing and then when we go away, it disappears. The organization will persist. So anyway, with that comment, here are some links that you can use to find out more about both QUDT as well as with PCA. And now I'm handing it over back to Andres.
Thank you, Steve. One thing I'd like to point out is that we've tested this process. So with colleagues from the ADAPT team, we did a gap check of the units of measure that are used in ADAPT and given its compatibility with ISO 11783, by extension, the units that are used in that system as well. And we found that there were 3 units of measure that are used in agri-food systems that we were aware of that were not already in QUDT. And Kelly Nelson, one of the co-chairs, technical co-chairs of the ADAPT team, actually went through the process of proposing the changes through pull requests and QUDT's GitHub and so forth. And we saw how it played out, and it was fine. So this is something that one of your software developers already knows how to do in your organization, right? It was quite pleasant to see that happen. Regarding TC347, going back to the beginning, what's this got to do with us? First, we're going to discuss this topic again at our plenary in 3 weeks in Cologne. We'll go into this in detail in the first technical session. This will likely be followed by a sort of lightweight ballot for an ad hoc group, like we usually do with new ideas. And this ad hoc group will clarify our needs. It will determine if QUDT can solve them. Spoiler alert, the work we've done so far is very encouraging in that respect. Then we draft a simple standard, something quite small, that shows how to use QUDT in our standards work, and so that we can then use that as a normative reference in all our upcoming standards to just standardize our approach to units of measure just through citing that as a normative reference in all the future standards we've got, and also to formalize that maintenance agency relationship that Frederick mentioned earlier, right, with POSC-CSER, because the way that works is that they enter into an agreement with the TC to maintain this controlled vocabulary, and they show what the process is, and we agree on how things will happen moving forward, right? And ISO retains, the right to get the data from them if for whatever reason POSC-CSER ever has to stop doing this. So all these standards are then protected, right? Then that group mindful of the fact that solving the technical part is usually only a small fraction of the total problem. They'll also determine what guidance and implementation materials we need to help our users implement the unit of measure system, and then they'll work with our AG1 on communications and AG5 on learning and growth, and anybody else appropriate to get those materials created. And Steve, can you take us to the next one?
Sure.
Thank you. So if you are a TC 347 member, you know how this works, but if you're not, how do you participate? Well, most of the work happens online. We have 2 plenary meetings per year where everybody gets together, but one of those is virtual. It happens in October, and the other one's in person. It so far has been happening in March. This year's is happening in Cologne in Germany from March 9th to 12th. And those are the plenaries. Most of the work, though, happens in working groups, ad hoc groups, and advisory groups that meet more often, but they set their own schedule. There's 2 ways of contributing. One, the preferred one, is through your national standards body. So your country has an organization, say ANSI in the US, or BSI in the UK, or DIN in Germany, or BIS in India, and so forth, that are the national standards bodies, and they are the ones that join ISO and that formally join the TC. They may delegate in another organization that is closer to the agri-food systems domain to create the country's positions and so forth. That's called the National Mirror Committee, right? So the best way to participate here is by joining that National Mirror Committee, and I can help you find yours. Just write me afterward. The other way is through a liaison organization. So we have 10 organizations that work with us. I mentioned Ag Gateway is one of them. The Ag Industry Electronics Foundation, AEF, is another one. International Society of Precision Agriculture, Young Professionals in Agriculture Development, YPARD, and so forth, right? If you're a member of one of those organizations, they may be willing to allocate you as a liaison representative into TC 347 as well, right? Then, that being said, there's multiple ways of contacting us. There you have an email address. I'll put my own email address as well. And we have a page in the ISO site. We have a LinkedIn page. We have a YouTube channel. So there's plenty of ways of contacting us, and please do, right? And so now we'll transition into the questions. And Martin Kraft asked the first one: how would one deal with necessary annotations to data, like the applied measurement procedure or standard, the quality of the data, and so forth?
Yes,
right?
I've got it. My answer on that, Martin, is to recognize that QDT, because it's expressed in a ontology language, it's possible to integrate it with other ontologies. For example, DQV is a standard from W3C for data quality. DQV, I repeat that, for attaching other documents. There are things like DCAT, of course, but there are other ways of extending the models to represent that. But then the whole business of measurement is in precision, etc., is beyond the scope of QDT. But there are other ontologies that address that, and maybe Steve can speak to some of those other ontologies for measurement.
Sure.
I'd like to jump in real quick, if I could, with some specific ISO information, and then Steve, you add commentary as you wish. from I mentioned that ISO 7673 Part 2 used QUDT among others, and the way that it does that is by separating concerns. So we have our data type definitions, same thing that ADAPT does or that 11783 Part 10 does. And those data type definitions might be associated with a unit of measure, either as a default or as the one that you're supposed to use, right? So the data type, the thing that says temperature or air temperature or vehicle speed, that might have a unit of measure associated with it. But the other things that you talk about, like the measurement procedure, the data quality, and so forth, are orthogonal to that. In 7673 Part 2, which is an implementation of ISO 19156 on observations and measurements, that is very explicit, where you have these things that are data quality elements, which works sort of the same way, where you have a definition of a data quality measure that's like your variable, and it might be, say, the percent of the data set that's complete, or the dilution of precision of a navigation system, and so forth. That might give you a number. That might be tied to a unit of measure, right? Where this is relevant, or not. It depends on the data quality measure, but something like percent might have a unit measure. So that's data quality. And regarding method, that's another orthogonal thing that is dealt with explicitly, right? Like you would have say, a code for an observation method, a code for a method in which you're building a um, probability distribution of those measured values, and another code for how you're um, sampling and building the statistic that you're going to report. Like, for example, saying I'm in a weather station, I'm measuring air temperature, and I have a code that says that I'm going to be measuring these air temperature values with a sensor. Then I have another code that says that I'm sampling this every 10 seconds. Then I have another code that says that I'm going to report the average temperature over, a 15-minute period or something like that. And then all that can get rolled into a code that represents 15-minute average air temperature at, 1.5 meters or so forth. Steve, I don't know if you have any more from the
Yeah, I
QD
mean, I
side.
was gonna first, there are two principles which we stand behind. One is the fact that the semantic web, these kinds of ontologies, are composable. As Ralph had mentioned, he'd mentioned another ontology for measurements, and there's smart sensor network, which is a different ontology. You can plug these together. That's one really nice thing about the semantic web. And what that supports is QUDT has a very defined scope, which is units and quantity kind, QUDT, quantities, units, dimensions, and types. We're going to build a wall around that. That's all we're going to focus on. We want to do it excellently. We don't want scope creep. So we'll take responsibility for that and let other people deal with measurement procedures and those kinds of things. So we've found our little sandbox. We're going to stick in it and we're going to do an excellent job in that. That's all I have to say.
All right, thank you. Do we have other questions? Okay, I have one. One of our experts before has asked about units ML, for example, and that's another system that's sometimes in the discussion. So, how do you compare to that?
Right. Yeah. Units ML is as the ML means, is the markup language. It's a way of identifying a unit, but it doesn't model the unit the way we do with pointing to linking to the quantity kind, dimension vector, etc. That's one limitation of that. The other problem is that units ML, much like UCUM, has multiple ways of representing a unit, which is convenient if you're just trying to identify something, but it does take its toll on interoperability because one person might use, as Andres had said at the beginning, an exponent, plus or minus exponent. And another way of representing that in UCUM is with a slash. There's numerator slash denominator. Um, and if you're just looking at the code, you might not recognize those are actually talking about the same thing. So it's not only, it has to be a unique identifier, and we insist on that. It's persistent, it's unique, and it's unambiguous.
Thank you. I'll ask you another question. At the beginning, when I was looking or going through those three conditions that seem appropriate for the industry to embrace a system, I mentioned that it would be optimal for the codes to be short, while at the same time something that is based on an ontology like um, QUDT tends to have longer identifiers because that identifier is sort of formally the whole URI, right? HTTPS QUDT.org/unit/ and then what, my community would call the code, right?
Right.
But we have spoken about a conventional mechanism for making that problem go away. Could you describe that a little bit?
Ralph, do you want to talk a little? Because we do have, as you say, the URIs now,
Yeah,
but
the NASA experience was to have encodings, and I just give you a little bit of history there. The parameter IDs on a launch vehicle represent the units in particular ways. But that led, as I said earlier, to an insight that we needed to have things that a telemetry packet could hold. And what we are busy with here is to take the uh, every unit, every quantity kind, and assign it a fixed length code. How many will we need? Well, if we use alphanumeric, we can have 36, which is the 26 letters of the alphabet plus 10 digits. 36 to the power 4 gets you enough, I think. If we have 4 bytes for it, yeah, 4 characters for it. We might only need 3 characters for it. So we are in the process with a change that's going on, assigning those codes that would be very necessary for telemetry, but also for Internet of Things, where you don't have enough resources to handle the what's called the local name of the query, the queue name as it used to be called, which is the name after the last slash in the URI. So we are going to have those compact codes. There are codes already, but we're going to go to a different coding scheme which has more extensibility, more longevity. Yeah.
right. So there'll
So
be a
it's
one-to-one correspondence there. Yeah.
so IoT is already quite big in ag and getting bigger and bigger. And so what I just heard you say is for those folks who are um, thinking about operations out on the edge and having to move data back efficiently because their bandwidth is limited or their data plans are not cheap. There's a nice way of packaging this into binary codes that are very efficient, and that's great. And I've peeked under the hood, and I know that you guys maintain um, mappings to UCUM, for example, and so I can imagine that this would be a very easy implementation. But also, in the here and now, the idea of splitting these URIs into a prefix and a particle, you already work with that too, right? Do you want to explain that a little bit?
Um, are you talking about, well, the prefix, you mean the namespace?
Yes.
Well, that's consistent with the standard practice in the semantic web that
Mhm.
every URI has a quote unquote local name or QE, as Ralph mentioned, plus the former part, right? So and usually, but not always, but in our case it is true, the URI, the Uniform Resource Identifier, can resolve to a Uniform Resource Locator, which means you plug that into a browser and the internet goes to the place that is identified in the first half, where the server, the server that will serve up that thing. So that is just normal, HTTP and web and semantic web practice. So we're not inventing anything there.
Excellent. So in other words, there's no need to wait for anything. Uh, what you have right now is perfectly usable for that purpose.
Right.
Then Hadi is asking from Florida if there's an ISO standard for measuring nutrient levels in soil, plant tissue, or biomass collected on farms, especially for raised bed tomato production in Florida, so that lab reported values, acceptable ranges, and measurement procedures are standardized. Well, Hadi, I'd like to point you to the work that Ag Gateway is doing with what was um, a sort of standalone informal organization before called Modus. And Modus, analogously to how QUDT is merging into POSC Caesar, Modus merged into Ag Gateway. And they have a large, very well curated um, vocabulary of laboratory test codes that correspond to the tests that you get from the agricultural labs, and then you can use like 7673 part 2 to encode those values. Modus also has a schema that you can use, right? And Ben Craker there from Ag Gateway in the chat gave you a link to it, and um, you can ask him for details afterward. I can hook you up. Mason from Sudan points out that in some places they apply urea granules directly to the crop by hand. That is true. People that are interested in how to represent those um, field operations, I would direct you to ad hoc groups 8 and 9 and also to the ADAPT framework. Okay, we've got 2 minutes left. Let's see, do we have any final questions? Okay, Mason says wants to be a participant. That's great. We need to get you into the committee. And all right. Steve, Ralph, Frederick, thank you so very much for your time and for your efforts and patience leading up to today. And you know that we don't plan to leave you alone exactly moving forward. I'm sure this ad hoc group will very much need your guidance as well. So thank you.
It was a pleasure to reach out across the world like this. Thank you, Andreas, for making all the logistics happen so smoothly. Thank you.
Yes. Talk to you soon.
Thank you. Goodbye, everyone. Thank you very much.
Bye-bye.
Please answer the survey.